Welcome again to Engineering Science 211, Material Safety and Equipment Overview for Nanotechnology. We're in Unit 2, and we're talking about infrastructure. And we know infrastructure means facilities and equipment, and we've been talking about those in some detail. We know we need facilities because we have to have a place to make materials, to make devices, to make structures, so we need some place. But we also need the facilities for contamination control, for safety reasons, for environmental impact reasons. So we know we need infrastructure, we need facilities, and of course we need equipment, we need the tools with which we make things. So we talked about facilities, clean rooms, hoods. We talked about equipment. We've talked about vacuum-based systems in particular so far. And we have decided that we better know a little bit more about vacuum itself. So we've gotten into vacuum science and technology in the past 3 lectures. So in Lecture 4, Lecture 5, and Lecture 6, we've been focusing on vacuum technology. And in Lecture 6, the last lecture on this topic, we're going to talk more about vacuum systems, and this will be Part 3, getting into the details of vacuum science and technology. So in this Lecture 6, we're going to be talking about vacuum pumps and vacuum leaks. Up till now, in Parts 1 and 2, we've talked about what is vacuum, vacuum systems. We've talked about how to measure pressure. We've talked about mass flow controllers. We've talked about valves. Today we're going to talk about vacuum pumps, the things that make the vacuum. Now we're going to talk about leaks, the things that drive people crazy when they're trying to control a vacuum and there's some leak problem. Vacuum pumps are selected and used based on a number of criteria. In other words, as we'll see, there's a lot of different types of vacuum pumps. And so you have to decide what vacuum pump you're going to select and why you selected it. So one of the first things you have to consider is what vacuum range are you trying to achieve? And what gases will be pumped through this pump? In other words, are they going to be gases that could react with the pump? Are they going to be dangerous gases? So we have to consider that. We have to consider the pumping speed. How quickly do we want to be able to evacuate a region? That is, how quickly do we want to be able to control the pressure, reduce the pressure? We want to look at the overall throughput. Same issue, how fast do we want to be able to move gases in and out of a processing chamber? And then how fast do we want to be able to move samples in and out of the chamber? How fast can the chamber be pumped down after a sample is completed? This has to do with the ever-present engineering issue of cost and how many products can you make in a unit time. You can't be spending a lot of time pumping systems down, and so that's an overall issue. And then, as we said, you have to worry about the gases you're pumping. Some can be corrosive. Of course, you have to worry about cost of the equipment, which includes not only the initial purchase price, but also the cost in maintaining the piece of equipment. And you have to ask the question, especially when you're interested in production, is the downtime that's going to come with any piece of equipment, is the downtime acceptable? Now, here's a good question. Can you get positive answers to all these different issues with all pumps? And the answer is, it depends on the situation. So we'll take a look at that, and we'll look at the operational physics going on in all these different kinds of pumps that we're about to survey. Well, here's one of our charts, which shows the typical ranges for vacuum pumps. So you'll recognize this chart. We've used it before. Atmospheric pressure is over here. Low vacuum is here. Rough vacuum is here. High vacuum is over here. And ultra hot vacuum is over here. And we recognize, we've used the scale before. So we're going to use that as the ordinate, and the abscissa will be the names of the different kinds of pumps. And so here we introduce the pump names: mechanical pumps, diffusion pumps, cryogenic pumps, and turbomolecular pumps. We'll also talk about titanium sublimation pumps. Those are not on the scale here, but those tend to be operating in the ultra-high vacuum range also. So we'll talk about titanium sublimation pumps also to add to this list. So in this lecture, we're going to strive to look at 5 different types of pumps. Vacuum pumps, well, what is a vacuum pump? Just to make sure we're all on the same page, it's the apparatus used to remove gas particles from a process chamber. The gas particles are the molecules, the atoms, maybe even some dust particles, maybe even some bacteria, viruses. We want to get them all out of the processing chamber, thereby reduce and control the pressure. The vacuum pumps used in nanofabrication, the ones that we saw in that previous table, we can break them into 2 categories. Mechanical pumps, which are really good for low vacuum and roughing pumps, and then high vacuum pumps. Mechanical pumps are very simple. They're used to reduce pressure to a low vacuum state, well, down into the low vacuum state of 10 to minus 3 torr, which, as you'll recall, is just the border of these man-made definitions of low vacuum, high vacuum, and ultra-high vacuum. So this is just at the border, and so a mechanical pump can take you down to that border. Mechanical pumps are used to initially reduce pressure in a system where the pressure is high. So in this case, this really shouldn't be high vacuum, it should be high pressure system, and by that I mean close to atmospheric pressure. So they're good in a situation where the pressure is atmospheric or maybe a little bit below that, and they operate very well in that situation to lower the pressure. They generally have an oil-sealed rotary vane, and that's generally the structure, and they can pump then water and residual gas down to about 10 to minus 3 torr. So the mechanical pump looks like this, and it's a very simple pump. You can see that the vane, the actual pumping is done here, and the gas enters chamber A. Excuse me. Gas enters the chamber A, and then chamber A here, and it's compressed by the rotor. This is the rotor, and the vane. This is the vane, and expelled to the atmosphere by the discharge valve. So it's exactly expelled. It's pushed around and then expelled out here. So the molecules are actually captured and pushed around and expelled. So they get, as this goes by here, the molecules get trapped in here. This goes around and then pushes them out. And then meanwhile it's busy trapping some more. This comes around, pushes them around, and they're pushed down. So this is where the vacuum is up here. And you're capturing the molecules into here with this vane pushing them out here. It's kind of like a rotating door. You know, when you go into some buildings, they have these rotating doors. And you go in and you turn around and you get pushed out. It's kind of that kind of idea. So it's a very, very simple mechanical pump. And there's an airtight seal around the structure, and the vanes and the surfaces between the rotor and the housing are sealed by low vapor pressure oil, which also serves to lubricate the pump. So you have to worry about sealing here. You don't want these molecules to get back over here, so you have to worry about sealing here. Then you have to worry about mechanical friction, and so that's all taken care of by a low vapor pressure oil. Low vapor pressure oil means that the oil, the molecules that make up the oil, there's a very low tendency for them to become vapor and come into the environment here. Well, mechanical pumps have, as always, as with everything we see, advantages and disadvantages. They can pump from atmospheric pressure, and we said that's where they're used. They're used to, at atmospheric or just below atmospheric, they're used to pump the system down as far as maybe even 10 to the minus 3 torr. That is, as far as perhaps a millitorr. They're rugged, they're low maintenance, low operating cost, low initial cost, they're fairly cheap, they have a long life, and they can be quite small. And by the way, one of the earlier lectures I mentioned, if you'll remember, a very simple use of vacuum pumps has nothing to do with creating processing environments. Here's a processing environment. This is where we're doing all the work to control the molecules and everything. But another use of vacuum pumps is to take a block like this and put holes in it. We talked about that before. And then have a vacuum pump down here that's pulling on this so that you can hold a sample here. And you can say, in other words, you hold the sample down. This is one way of holding samples down in a number of situations. And so a mechanical pump is often used to do that. But no, we're not focusing on that. We're talking about the processing environment and controlling the process environment. The disadvantages of mechanical pumps, they can backstream oil. The oil we talked about, that can backstream. What we mean by backstreaming is the oil can wind up going back into the vacuum. You can see the molecules bouncing around, and some of them may make it back into here, oil molecules. We said it was low vapor pressure, but there could be some oil molecules that get back into here. That's disastrous. So we have to worry about backstreaming. They can be noisy. Their efficiency decreases below 10 to the minus 1 torr, and you can see why. It's just hard for them. When this rotor comes around to here, there just may not be that many molecules to trap. And they can be sensitive to particulates. You can see why that can be the case, because things can get ground up in here. They really hurt the pump. So if you have some process that's producing some particulates, then you have to be very careful here. And they generally have low frequency vibration, which is good. The low frequency vibration is a good attribute, so that belongs over in the advantages category. Backstreaming, the oil coming back, that's potentially a major source of contamination. As we said, that can be very, very bad. You can imagine oil molecules getting on the surface of the sample you're working so hard to control. And so the pump oil can volatilize, that is, some of the molecules can turn into a vapor, and they can bounce their way back to the process chamber. That's not good. As the chamber pressure decreases, backstreaming becomes a bigger threat, dependent upon the vapor pressure of the pump oil, obviously, because that's the source of the molecules, the pump oil. Low vapor pressure, less of a problem. And this problem causes a lot of companies to switch to dry pumps, which don't use any oil at all in the pumping process. So there's a dry pump version of the pumps for this pressure range, and they're becoming increasingly popular. Well, by the way, as the chamber pressure decreases, backstreaming becomes a bigger threat, and that's because here's the piping, if you will, leading to the pump. If the pressure is lower, then the oil molecules will encounter fewer collisions. They won't collide with other molecules. They might collide with the walls, and so they'll get in here easier. If the pressure were higher here, then they would collide with these molecules and maybe bounce back. So as the pressure gets lower, backstreaming becomes a bigger threat. And that we can understand, as I just explained, by the molecules and the collisions that take place. We know fewer molecules, longer mean-free path for these oil molecules, better chance they're going to make it back into the vacuum system. Pump oil, of course, is used in these systems. If you have a situation where the vapor pressure requirements are not severe, if you have that situation, then you can use a standard or hydrocarbon-based oil. However, you may have situations where the vapor pressure is a big issue, and we'll discuss those in a minute. If you're using the hydrocarbon oil, known as mineral oil, it can be unsuitable because the vapor pressure can be too high. It can be unstable in oxygen environments. Maybe you're doing some processing where oxygen is present, and so the oxygen can obviously react with the hydrocarbon. And at higher temperatures, the hydrocarbons, just because of the temperatures that might be involved, can break down and crack. And that is decomposing into smaller molecules. So you might want to look at not using hydrocarbon-based oil. If vapor pressure requirements are not severe, mechanical pumps can use them. But if the vapor pressure becomes an issue, then you have to think about moving to synthetic oils. And these have been developed to overcome the shortcomings of the hydrocarbon oils. And synthetic oils have low vapor pressure. These have been engineered to have low vapor pressure, high viscosity, and a high degree of oiliness, so they're really good lubricants, and chemical inertness. So you can use them to a certain degree in situations where you're pumping gases that may be reactive. Fluorochemicals, which is a type of these synthetic oils we're discussing. These are characterized by their inertness to a wide variety of chemical compounds. That is, inert means they don't react with, react with things. So these fluorochemicals, which are a type of synthetic oil, these can be very suitable for high oxygen environments. And there are two prominent commercial varieties of these completely fluorinated oils. One is called Fomblin, and the other is called Krytox. So these kinds of oils, synthetic oils, and they may be of need in situations where you're pumping gases out of a vacuum system. Here's your vacuum system. You're pumping these gases, and there may be in here a situation where whatever is flowing through here, something's coming in, you're doing some processing, this effluent could react with the pump. And so you have to look at the use of synthetic oils in that case. And of course we know the pump needs oil if it's a regular mechanical pump. We talked about the function of the oil in sealing and in friction reduction. So the mechanical pump system here here's a better schematic than what I've been drawing. Here's your processing chamber. Here's a thermocouple for measuring pressure. Here's a valve for open this valve and use this to pump the system down. You may have a trap here to control what's the effluent. Here's your mechanical pump. You recognize the vein trapping the molecules and pushing them out like the vein in a door in a department store. A rotating door in a department store, as I was mentioning. Here's another thermocouple, a gauge to keep track of the pressure. So you can see here that you can pump down. You can have gas coming in for some processing. You can be continuously pumping. If that gas is a problem, you might want to have synthetic oil here. Once you do your processing, you can close this valve. This molecular sieve here, by the way, there can be traps here, but a molecular sieve here is to stop the oil from backstreaming. You can isolate this pump. You could then backfill in, say, nitrogen back in this way. You can then have a load lock here. So you could take your sample, move it into here, close this up. This would be pumped down. Then you could put nitrogen into here to backfill, then open the door and take your sample out. Anyway, we see a mechanical pump is one way to achieve vacuum And as we said, this is vacuumed down to, say, 10 to the minus 3 torr. That is down to a millitorr. High vacuum pumps, now we're moving into the regime below 10 to the minus 3 torr. And sometimes these are, in fact often, these are used along with the mechanical pump. So you rely on the mechanical pump to bring the pressure down from atmospheric pressure or near atmospheric pressure. You rely on the mechanical pump to bring that pressure down, because remember, mechanical pumps are very good at atmospheric pressure and near atmospheric pressure. So you can rely on the mechanical pump to bring the pressure down, and then you would use a higher vacuum pump to get the pressure below 10 to the minus 3 torr. So although the previous sample here, previous sketch only showed a mechanical pump, in many processing systems you'll have the mechanical pump to bring the pressure down initially, and then some other type of high vacuum pump to bring the temperature to bring the pressure further down. So high vacuum pumps are used when you want to pull that pressure down below 10 to the minus 3 torr. And they're made of materials that will not outgas. Obviously, you don't want gases coming out of the pump, because at low pressures, they can make their way back into the processing chamber. Because as we know, fewer collisions, longer mean-free path, the molecules can make it back to the processing chamber. So often you'll see the use of stainless steel, titanium, Kovar, nickel, borosilicate glasses, ceramics, tungsten, gold, and oxygen-free, high conductivity copper. These are some of the materials that are used to make these high vacuum pumps. So you have to really think about what you're using to make the pump itself so that it is not a source of problems. Now, high vacuum pumps come in several different varieties. The oil diffusion pump, the cryogenic pump, the turbomolecular pump, and the one that was not on our table at the beginning of this lecture, but the one we said we would talk about also, the titanium sublimation pump. So these are examples of high vacuum pumps. And you can see this one uses oil, so we need to really think about that. We just were talking about the problems that can be encountered with oil. This one uses low temperatures to actually cause the molecules to freeze on a surface. And we're all familiar with taking a glass of cold water, and on a humid day we've all seen the water molecules condense on the side of the glass. Well, this uses that idea, except at very, very low temperatures. This isn't water, this will be helium, and you can get lots of molecules to condense here, and so you can pump that way. Turbomolecular pumps is sort of like a jet engine kind of idea, big turbine to pull molecules. We'll talk about this more. And the titanium sublimation pump, that makes use of the fact that titanium loves oxygen. And so, since oxygen composes 20% of the atmosphere, when you get down to high vacuum situations, titanium sublimation pumps can be great in further pulling down the pressure by titanium sublimating, that is, turning into a vapor, and then the vapor reacting with oxygen. Then you form titanium oxide, which then coats out, and you have then used the titanium to pump. So engineers, scientists use all sorts of different ways to accomplish pumping in the higher vacuum regimes. The fusion pumps, that's the one that uses oil. This is uses a vapor jet, which transports gas by momentum transfer on collision with a vapor stream. So the idea here is, here comes the incoming gas from the incoming molecules from the vacuum, from your vacuum chamber over here. And what you do is you create a jet of oil shooting down here, which actually entrains these molecules. They get entrained in this jet of oil, come down to here, and then you allow them to, the molecules that have been entrained, you allow those to escape. In other words, you pump them, they leave, and then the oil is recycled back up through here. So it's an entrainment, or it can be looked at in a more sophisticated, from a more sophisticated point of view, as momentum transfer from the jet to the molecules coming in, forcing the molecules to go in this direction. And the oil is heated in a boiler until it vaporizes to produce this jet. Well, you can see that we really need to think of what is this oil made of to make sure the oil isn't going back that way. Here we have in this view graph a schematic of a diffusion pump, and let's just talk about how it works. As you see in this schematic, the inlet is coming from the vacuum chamber, so the gas molecules are bouncing their way down to here, undergoing collisions, bouncing into walls. Then the oil jet is set up to capture those molecules, entrain them, give them momentum that really directs them this way. The molecules then bounce around and get into here. You can see that there's baffles here, and the pressure of these molecules will build up, so then they'll go out this outlet. Well, that's generally the way the jet is used to capture the molecules, which are happily bouncing their way into here from the vacuum chamber, which is up here. Diffusion pumps have a number of advantages. They're reliable. They have no moving parts. We just saw there's nothing mechanical there. They're inexpensive. They're relatively quick with a good pumping speed. They have high throughput. In other words, they can really handle a lot of gas and get it through the system. And they have low cost. Disadvantages, well, this is not surprising. They're prone to backstreaming. And backstreaming, of course, comes from the oil. So that's a pretty obvious problem that you have to watch out for. They're not suitable for corrosive gases or oxygen gases because those entities will react with the oil jet. This is hot oil. They require cryo-trapping. That is, although I didn't show it in that schematic, there's generally a trap between the diffusion pump and the vacuum chamber itself to try to capture oil, try to cool it down and capture it before it makes it into the vacuum chamber. Remember, we have oil molecules. The occasional oil molecule will be bouncing its way back toward just because it's bouncing everywhere, and just some of them will happen to go towards the vacuum chamber, the processing chamber, and we can use cold temperatures to trap those. And then you have to have something to pump on the diffusion pump itself. You need a mechanical pump here to keep this going and keep it out. So you need a mechanical pump here. So a diffusion pump requires a backing pump, generally a mechanical pump. So the oil issue again has caused the development of alternatives, and these alternatives, a common one is the silicone-based oils, and these are made up of repeating groups of silicon and oxygen, and they're used widely in diffusion pumps because they allow you to then introduce. They can withstand an oxygen type environment. They have low vapor pressure, which of course stops the backstreaming or reduces it, and they're stable even though these oils are being repeatedly heated. This particular type of oil is stable. However, their lack of adhesion and inability to form a film on steel limits their usefulness in other pumps. So they're not very good for any kind of lubricating function, but they are good in this oil jet function. So here's the overall system now. I put it all together. Here's our chamber where we're doing our processing. This R should be up here. So this is full of our little gas molecules bouncing around. Very few, we hope. Here's an ion gauge keeping track of what's going on, so we know this must be in a low pressure regime. This must be low pressure, means high vacuum. This must be high vacuum, or maybe even bordering into the ultra high vacuum. This is your oil jet down here. Here's your liquid nitrogen trap to try to stop any oil molecules from getting up here. You want to freeze them. This is our glass of cold water idea, where water vapor sticks on the side. Here the glass of cold water is liquid nitrogen, and the water, quote unquote, is not water, it's liquid nitrogen. And the coating on the side, we'd like to be oil molecules so they don't get up into the vacuum chamber. We're pumping on the system with a mechanical pump so that when the molecules are here, and they're detraining, if you will, we capture them and pump them out. And you can see the different valves used to control this. You can see thermocouple gauges, ion gauges, and of course we expect that there's probably some processing going on in here, so there'll be additional inlets for processing gases. There may be a load lock here to put the samples in and out, and so on and so forth. But you see the general components, the fusion pump being backed by a mechanical pump. Cryogenic pumps. This is literally the water glass kind of idea. Well, not literally, because the water is generally helium, liquid helium. But we're capturing molecules on a cooled surface, just like you can capture water vapor on a cold glass of water, the outer surface. Here we're going to capture water molecules on a cooled surface by weak van der Waals forces or other types of forces. And van der Waals forces are just when a molecule comes up to a surface, if you can get it to lose its energy and cool down, which you do by having a very cold surface, then you might be able to get the molecule to stay there because of weak interactive forces, chemical forces between the electrons. You know, a molecule has a cloud of electrons. Interaction between those electrons and the electrons that constitute the surface, that interaction, that kind of weak interaction may be sufficient to get the molecule to stay there. And those types of cloud-cloud interaction, that's called a van der Waals force. And so you can get cryo of course means low temperature, cryocondensation, cryosorption. Sorption is when you have a surface here that may be rough, and so you get things absorbed into maybe nooks and crannies here, and you may have actually things getting trapped in here, cryotrapping. So in essence, cryogenic pumps will use liquid helium, as we said, or liquid nitrogen to cool and segregate gases. And it's a capture pump. It's just a pretty neat idea of taking something you see every day, well, maybe not every day, but especially in the summer, cold glass of water causing molecules to condense on the surface, taking that idea and turning it into a very sophisticated cryopump. Cryopumps are designed with a central fin stack, and the gas from the chamber collects on the vanes of this stack, removing the gas molecules from the system, reducing the pressure. Obviously, if you take the molecules out of the system, you've reduced the pressure. There aren't as many running around anymore. And then that group of fins is cooled by the helium to keep it active as a surface upon which the molecules will condense. Cryopumps can very efficiently pump water vapor. This is no surprise. We know a cold glass of water can pump water vapor. Liquid helium must do an incredible job. And water vapor can be hard to pump because water molecules are pretty light. And so it's tough to change the momentum. And changing the momentum is what a mechanical pump does. It's what a diffusion pump does. But we're not relying on changing the momentum in a cryopump. We're relying on getting them to stick to a surface by van der Waals forces. And so cryopumps are very, very good at pumping water vapor. Here's a depiction of a cryopump. And you can see the pumping's actually going on in here. Again, this is a capture pump. And so you capture. Obviously, you have to release what you capture. So when you're done pumping, you could close a valve up here, and then you could allow this to warm up. The molecules come off the surface, and you can pump them out. That's called regeneration. So these are generally not systems where you constantly pump on them. You generally do not constantly pump on them. You generally use them, close them off, bring the temperature up, then pump off what's been captured, and that's called regeneration. So cryogenic pumps have a lot of advantages. They're high speed, high throughput, clean. Well, they're clean. There's no oil, nothing that backstream. Remember, the liquid helium is there, but it's inside the veins. Low operating costs, don't require backing. Remember, they don't have that pump to back them. You don't have that constant need. Disadvantages, they require regeneration, because remember we said they capture, then you have to release what's been captured. You may use a backing pump then, you may not. They definitely require maintenance because you're running a compressor that's producing liquid helium, and that's not easy technology. As we all know, compressors can give out, like in air conditioning systems. So you have to make sure the compressors is operating correctly, and you have to do a lot of maintenance on the compressor. Now the fluid, for example helium, has to be very pure, and there's a possibility of explosion. That is, you're trapping the gases down there. You have to be careful as you heat the system up, for example, during regeneration, that the gases there don't chemically react. You could even have an explosion. So a cryo system looks like this, and you can see the processing chamber. There's that compressor that's producing another R that's not where it belongs. You can see the compressor, which is cycling the liquid helium, let's say, into the cryo pump. You can see this is pumping down on our processing chamber. Then in this particular case, we see the mechanical pump there for regeneration. And so this would not be in play when you're pumping, but when you want to regenerate this system, you would probably have to do, well, you're not probably, you do have to do that every so often. You would make sure this high vacuum valve is closed. You bring up the temperature and you can pump off what's evolving off the system if you decide to back it up. But you'd only need to do that when you're regenerating. So turbomolecular pumps, affectionately known as turbos, and it's a lot similar to a jet engine. You know how a jet engine transfers momentum to the air molecules at atmospheric pressure, or maybe a little bit below atmospheric pressure, but 37,000 feet, definitely below atmospheric pressure. Because when we say atmospheric pressure, we're talking about at sea level. But like a jet engine, transfers momentum to the particles and then shoots them out the back end. So that's essentially how a turbo pump works. So it's a series of blades with openings that allows the molecules to come sashaying in, if you will, from the vacuum system, and they pick up this momentum and go flying out. And the blades are rotating at very high speeds, 24,000 to 40,000 RPMs, revolutions per minute. And so they work, on, again, as we've seen in a number of pumps, on the idea of momentum transfer. For example, we saw momentum transfer being so important in diffusion pumps. So a turbomolecular pump has the molecules from the gas chamber. They are flying around, and they encounter the first blade, gain momentum in the direction we want them to have momentum in, and then they start moving through this succession of blades. The momentum direction is downward to the next blade. This assumes that the pump is oriented this way, so downward. So this is composed of the blades. This is not drawn correctly, of course. The molecule comes in, bam, it shoots it down, and then out like a jet engine. So that's how we remove gas from the processing chamber up here somewhere. No oil, looks very clean, good pumping system. This gives you an idea of the blades and how sophisticated this is. This gives you another idea how sophisticated this is. And you can see the similarity to a jet engine. This, of course, is the casing. Here you see the casing present, and the blades are inside the casing. Turbomolecular pumps have certainly have advantages. There's no oil involved, there's no backstreaming, it's not an issue. They're able to handle corrosive gases, high oxygen content environments. It's not a problem. They can handle high throughput, fast startup, constant speed, constant pumping speed. So very, very nice systems. And unlike cryopumps, they do not require regeneration. Disadvantages, they're not cheap. They have a short lifespan. Imagine something that is working on these blades flying around at 40,000 RPM, and you can see why lifespan can be an issue. Bearings are an issue. They cannot operate at atmospheric pressure. Unlike a jet engine, these need, let's say, a mechanical pump to bring the pressure down, and then they can then come in when the pressure has been sufficiently reduced. So they can't be used just to pump starting at atmospheric pressure, unlike a jet airliner engine. They're designed to pump at lower pressures. So you need another pump to bring the system down. Then they also need a backing pump, and they don't pump hydrogen and helium well, and that's easy to understand. This is a momentum transfer pump, and hydrogen and helium don't have much momentum. They don't have much mass, so it's tough to get those to go where you want them to go. So here is a turbomolecular pump being used with a processing system. Again, the R here should be up here, and then we have our gas molecules bouncing around in here, hopefully very few of them. We have the turbo pump pumping on this. We have the turbo backed. We have a system where we can use this pump to bring the chamber down to a pressure where the turbo can operate. Once the turbo is operating, we can change the valving here to use this pump to back the turbo. So that gives you an idea of a turbomolecular pump system in operation. And you see, of course, all the valving necessary, as in any processing application of vacuum, all the valving necessary. And this is a simple application because we haven't shown the distinct possibility that there's processing gases coming in. We haven't shown the distinct possibility there's some kind of a load lock here to load the samples in. But this just gives you an idea of a basic turbomolecular pumping system configuration. Lots of gauges. The ion gauge, because this is where the low pressure is going to be. This is going to be the high vacuum or ultra high vacuum region. The thermocouple gauge for when you're beginning to pump there, and you can see here the pressure should be relatively high because mechanical pump is pumping on what's coming out of here, the effluent, so you can use a thermocouple gauge there, and as I said, all the necessary valving to be able to do what you want to do when you want to do it. So we've talked about vacuum pumps. I want to just mention a titanium sublimation pump one more time just to complete that subject. And again, just to remind you, that is another one of these dead-end pumps like a cryo pump. And as I said, it uses some kind of a titanium source which is volatilized, so you have some titanium vapor, and it pumps by molecules coming in. In particular, it's very good for pumping oxygen. As we said, titanium loves oxygen. It forms TiO2. This will then coat out in the chamber, and you've trapped the TiO2 here. So this type of pump is a dead-end pump. You're going to need other pump systems to get rid of the water vapor, get rid of other molecules. This one comes in very, very good for pumping oxygen. Very, very good at ultra-high vacuum pressures, but it has to be the chamber has to be brought down into this low pressure regime, into that low pressure regime before you can use this pump. So it's a dead-end kind of pump, as I said, like a cryo pump. Unlike a cryo pump, You don't have to bring it up to room temperature. It operates at essentially room temperature, but you do have to worry about coating, the coating here and what you have trapped in the coating, and perhaps recoating this to make sure that it doesn't become a source of outgassing and molecules working back into the ultra-high vacuum region. So you do have to control in particular the walls inside here, to make sure they don't become a source for outgassing and molecules coming back. But it's a very simple pump, very, very good pump for pumping oxygen. So let's talk about vacuum leaks now. Vacuum leaks are defined as a rise in pressure towards atmospheric pressure after a vacuum has been achieved. So in other words, you have a vacuum chamber where you're going to do some processing, and you pump it down to a certain pressure, but then you notice the pressure isn't steady, or you notice that you can't pump it down to the pressure you normally can pump it down to. Perhaps this vacuum system operates at 10 to the minus 7 torr. You find that you can't pump it down to 10 to the minus 7 torr. Or you find that when you pump it down to 10 to the minus 7 torr, which we've called the base pressure, the pressure, the lowest pressure you want to get to start your processing, you find that when you pump it down to 10 to the minus 7 torr, that it doesn't stay there. You find that the pressure rises, so there's some sort of a leak present. So it's impossible to achieve a perfect vacuum where there are no gas molecules present, because there's always going to be gas molecules coming from somewhere. They're going to be coming in through seals. There's going to be molecules coming off of the very materials that constitute the vacuum chamber. So you're always going to have issues. Molecules leaking in from the outside, molecules coming from the very materials that constitute the vacuum chamber. So leaks are divided, because of these sources, into two types of categories. One is the virtual leak. It's real, all right, because the pressure goes up, but it's called a virtual leak, and I'll make the distinction as to what that means in a minute, or the real leak. So let's just talk about what are the things that can go wrong here in a vacuum system. So here's our vacuum chamber here, and we're worried about what can go on. So this is our vacuum environment inside here, and this is the outside, and here's the wall that makes up the vacuum chamber. So what sort of things can happen? Well, at the end of this wall here, maybe there's a seal, and so maybe molecules from the atmosphere can work their way through the molecules that constitute the seal and make it in. Maybe they can actually be in the metal wall here, and maybe they can somehow desorb off the metal wall surface, or perhaps some of them can even make it in from the outside. Remember, atoms and molecules are always moving, just the degree to which they're moving. In a solid, they don't move very much. In a liquid, they move more. In a gas, they move a lot, as we've talked about. Those are the distinguishing features of those types of materials. So even in a metal, in a solid metal, the molecules are moving somewhat, and it's possible that a molecule can pick up enough energy to make it to the surface and get into the environment that we're trying to create with the vacuum. It's possible the molecule may even make it all the way in from the outside. And the materials that make up seals, as we said, these are the softer materials. They may be more permeable. They may be a source of molecules making it in from the outside. So those are real leaks, real sources of problems. And we can have things that are stuck on the walls. Here's more wall here, and there can be materials on the wall from the past use of this chamber. I always say that the vacuum chamber has a memory, and this chamber was used for something else. Some of these molecules and atoms may be on the wall, and they too may volatilize and come into the vacuum system. Another source of problems. And that's a virtual leak, because nothing's really coming from the outside. These things, where something comes from the outside, those are real leaks. It comes through the seal here, for example, that's a real leak. But if molecules come off the condensate, that's a virtual type of leak. It's not coming from the outside. And there can be all sorts of things, some kind of dirt in the vacuum system which can volatilize. It could be some kind of crud here because we weren't careful. There can be particulates from the previous processing that are producing particles that are going into the vacuum and moving around. Particles can be coming off of here. We can also have a virtual leak caused by something as simple as the threads on a screw. Because if that screw is put in here at atmospheric pressure, which it probably was, right, then it can have air molecules, does have air molecules trapped in here, and eventually they'll get out, and that's another source of a virtual leak. So we have virtual leaks here, virtual leak here, virtual leak here, real leaks here, and real leaks here. All of these things are going on, and can cause tremendous problems. So if you're looking at low vacuum range, you can have, and then this is high vacuum, this is ultra high vacuum, you can look at problems from condensation on the walls, not just water vapor, for example. You can look at particulates that could be around. You can have very large leaks, seals. These will really show up even in low vacuum. You can have water that's tied up maybe here, or maybe in here that comes off. You can have backstreaming of oil coming up. You can have all these things contributing to problems achieving just even a low vacuum. Then if you try to have, if your ambitions are higher and you're trying to get a high vacuum, then you can have elastomers outgassing, that is molecules coming out of, say, this material that constitutes the seal. You can have vaporization. Some of this condensate, some of these molecules might vaporize. You can have surface desorption, things on the surface, some of the, all over the place here. Some of those can vaporize. These are problems. Surface desorption, again, things that are on the surface from previous processing, things that are on the surface from previous exposures to the atmosphere, they can come off, desorb. Then if your goals are very, very high, you're looking at ultra-high vacuum, you can have problems of diffusion through the metals that make up the wall. You can have permeation through that metal coming all the way through. These are all the things that are possible that can cause you real leaks or virtual leaks. So a virtual leak is something where the supply is basically limited. There's only so much stuff that can volatilize. A real leak, the supply is essentially unlimited because the supply is the atmosphere. So a real leak is any pathway that a gas molecule can travel from the outside of a vacuum system, that is from atmosphere, to the vacuum system, to the vacuum chamber inside. So there can be gasket problems, gasket isn't sitting right, pumps aren't working right, lots of things that can cause real leaks. Virtual leaks, as we said, that's a limited supply that can volatilize, a limited supply of molecules. It's completely internalized phenomenon. It's not coming from the atmosphere. And the leak path originates on the inside of the system rather than the atmosphere and causes outgassing of materials. Outgassing is a fancy word for some of the molecules in the material pick up enough energy to turn into vapor, that is, turn into gas in the vacuum chamber. Contamination, we said that contamination can, some of it can turn into a vapor going into the vacuum system. You can have residual water vapor that you just have a hard time getting rid of. And then you can have backstreaming of oil. That's another source of a virtual leak. Water contamination concerns. Water is, well, it's ubiquitous on this planet. It's all over the place. It exists as a vapor in the air at relatively large amounts, Water vapor tends to stick to the sidewalls of processing chambers, and it's particularly difficult to remove in a vacuum system. So just the water in the atmosphere can come and adhere to the sidewalls. Now, you don't see it. It's not like you're forming a film. It's not like condensation on a cold water glass. But you can still get molecules to sit on the surface and adsorb on the surface. So when we say something adsorbs, and then we say things absorb, a little bit of Latin. Ad means it just sticks on the surface. Ab means it actually goes inside. So we distinguish between things that maybe just stick on the surface and other things that maybe actually diffuse inside and get inside whatever material this is. So water vapor can adsorb on the surface. It can even absorb in some materials. And it's common to see pump rates slow at various pressure plateaus. In other words, a 10 to minus 4 torr. If you're trying to get below that, oftentimes it's tough because this is when water vapor is starting to come off the walls of the chamber, and you're having a hard time getting it all off. In general, the lower the vapor pressure, the longer a liquid will tend to evaporate. We said that a while ago when we were talking about oils. Here's an oil. If it has low vapor pressure, then it's not that easy for the molecules to pick up enough energy and come off into the vacuum. So here's talking about water and the problems with water, and here's a comparison with other liquids. So the vapor pressure of water at 100 degrees C, and again, just remember room temperature is about 27 degrees C. So this is the boiling temperature. And the vapor pressure of water, the boiling temperature is atmospheric pressure. That's why it boils off. It's able to overcome atmospheric pressure and come flying off. If you lower the temperature down, the vapor pressure drops to this. You come down to close to room temperature, it's about room temperature, then you see the vapor pressure has dropped to 24 torr. And then you go down to, again, this is temperature in degrees C. So you go down to freezing, vapor pressure, you go down, you can see that at minus 78 degrees C, the vapor pressure is in the 10 to minus 4 range. So the molecules are having a very hard time coming off the water. Here the molecules are coming off the water very easily. In fact, we know how the surface looks violet with all the molecules banging into one another as they come off. Now if you look at some other liquids like benzene, at the same temperature, vapor pressure is 74. Wow, it's 10 times lower than water. If we look at 50 degrees, benzene is, ethyl alcohol is not too much different than water. Of course, we can smell alcohol, so we know molecules must be coming off. At 25 degrees C, methyl alcohol actually has a higher vapor pressure. So this is really easy to smell. At 0 degrees, water has this vapor pressure. Acetone has a very high vapor pressure, and acetone is very easy to smell. At minus 40, you see water pressure is 10 to minus 1 torr. Turpentine is about 4 torr, and anyone who's worked with turpentine knows that it must have a high vapor pressure. Lots of molecules coming off. So you can see that the vapor pressures, how they compare in this table. And this is an error, so I'm just going to cross that out. And here's high vacuum pump oil. We said that's really, really good. We try to stop backstreaming, and you can see how low you can make the vapor pressure there. And here's some simple system diagnostics. Just an idea when you're looking at pressure. So what could happen? Well, here's the pressure, and you turn your vacuum system on, and the pressure starts dropping. This is what you expect, pressure versus time. And what can happen, though, is that you can see that it's not behaving the way it normally does, and you can turn the vacuum system off, turn the pumping system off, rather, and then you can watch if it's a virtual leak. Since the supply is limited, it will stop. If it's a real leak, since the supply is not limited, the pressure will continue to grow. So you're pumping down, that's the way it should look. You notice there's something wrong, you turn the pumping system off. If it's a virtual leak, since the supply is limited, it'll plateau. If it's a real leak, it'll just keep going. And of course, a virtual leak, things are coming off, say, the surface. A real leak, things are coming from the atmosphere. A leak can be determined by performing an up-leak test. So you can process, you can undertake this test by taking a process chamber and pumping down to a desired base pressure, which is what we saw here. The chamber is isolated from the vacuum pumps and monitored for a rise in pressure. The degree to which the pressure rises determines the type of leak. So we said, looking at the behavior, you can figure out, ideally, what kind of a leak it is. You should be able to see either a saturating, a plateauing, or this telltale sign of infinite supply continuing to grow like that. So real leaks, that is leaks from the atmosphere, the rate at which the pressure rises with time will depend on the size of the leak. So you can get some idea of what kind of leak you have from that kind of information. In virtual leaks, as we said, the pressure with time will plateau, and the rise of these curves, or how fast this goes up, is a measure of how much outgassing is going on. Remember, outgassing is a fancy word we're using to say, hey, some of the crud on the walls is volatilizing, producing molecules running around the vacuum. Some of the water vapor on the walls is volatilizing and producing molecules in the vacuum. Some of the materials previously deposited in the chamber are volatilizing and forming molecules running around in the chamber. These are all virtual leaks, and the rate at which this goes up can tell you how bad these problems are. These are some examples of virtual leaks. We talked about that other example of a screw where you have molecules trapped from the previous history of the chamber being exposed to atmospheric pressure, and molecules getting down into, for example, the threads of a screw and then working their way out. Again, virtual leak, finite supply, plateaus. So you can have a combination. Naturally, of course, nature may make things tough for you, and you can have both types of leaks present. So you can have a situation where you have a virtual leak, and maybe that's dominating in the beginning. Then you can start to see it plateauing, but then it takes off. That means there must be a real leak. So the virtual leak would dominate up to here in this particular plot. And after that, the real leak is dominating. So you need to look at this in these plots and try to decipher. You have to be play detective and try to figure out what's causing the leak. Is it a virtual leak? Is it a real leak? Is it a combination? So we have completed lecture 6 today. We've talked about vacuum systems again. This is part 3 of our discussion of vacuum systems. We spent so much time on vacuum systems because they are so important in many types of processing tools. In lecture 7, we will discuss processing tools that do not use vacuum systems. But we discussed in previous lectures, these last 3, vacuum systems because so many processing tools do use vacuum systems. And what we covered was, in this lecture, we had an overview of vacuum pumps, looked at the different types, We looked at mechanical pumps. We looked at diffusion pumps. We looked at cryo pumps. We looked at turbo pumps. We looked at titanium sublimation pumps, just to name, well, just as examples of pumping systems, but those are the most common. And then we looked at vacuum leaks. What can go wrong? Virtual leaks. We looked at real leaks, and we looked at ways of being a detective and figuring out which type of leak one has in a given situation. So look forward to seeing you next time in Lecture 7 when we discuss processing and characterization, which does not involve vacuum systems.